All right, let's dive straight into this explainer right inside a high-stakes exam scenario where a tiny, seemingly harmless coding error just cost a student their entire grade boundary. Imagine you're sitting in the exam hall, right? The clock is absolutely ticking down. You've written what you think is a perfectly logical explanation of how a game stores the highest score in Visual Basic. You walk out feeling super confident, but on results day, you realize that specific question scored a flat 0. Why? Well, because you fell into a classic invisible trap that examiners literally see 1,000 times a year.
Take a look at this broken 0-mark exam answer. It represents a true memory palace trap, and it shows exactly why ordinary revision completely fails under pressure. On the surface, this answer feels right, doesn't it? It uses a variable to save the score so everyone can see it. I mean, in plain English, it makes total sense. But to a Cambridge examiner, this is just packed with red flags. It lacks technical precision, it makes huge assumptions about the programming logic, and it completely misses the scientific reasoning required for top-band marks. Ultimately, it's just way too vague.
In just a few minutes, I'm going to reveal the specific examiner clue that transforms this flawed answer completely into a guaranteed full-mark response. But first, we need to build the foundational framework that makes that clue incredibly obvious. If you don't actually understand the underlying mechanics of how data is handled in memory, well, trying to memorize the perfect answer is pretty much useless.
Section 1. Variables and constants defined. So let's look at the basic building blocks of our code to understand where that student went wrong. We really need to distinguish between the two primary ways a program remembers information. Think of variables as the programming equivalent of your own handwritten records. Imagine you're doing a science experiment, jotting down the temperature of a chemical reaction every single minute. You write down a list of temperatures, crossing them out and updating the values as you go. Variables do exactly this. They are small memory areas set up in your computer that store data. And crucially, this data can change or be updated dynamically while the program is actually running, whether that's from user input or a newly calculated result.
And this brilliantly illustrates the complete contrast with constants. While variables change, constants remain permanently fixed throughout your entire code. In Visual Basic, you declare them using the keyword const. A massive, unbreakable rule to remember here is that a constant absolutely must be assigned an initial value at the exact moment you create it. For instance, setting pi as 3.1415. Once it's set, it is locked in for good. The program cannot accidentally overwrite it later.
Now, Visual Basic is actually pretty forgiving. It lets you declare variables without specifically stating what type of data they're going to hold. But listen, just because you can doesn't mean you should. In fact, examiners desperately want to see something called strong typing. This is the practice of explicitly defining the specific data type, like an integer, a string, or a decimal, right when you declare the variable or constant. Why does this matter? Because it allows the compiler to instantly check for data type mismatches, preventing errors before the program even tries to run. And honestly, it just speeds up the execution of your code.
So, another crucial point is how we actually name these memory areas, which we call identifiers. Using crystal clear identifiers makes your code infinitely easier to read and maintain. And spoiler alert, that is exactly what examiners look for when grading algorithms. You have to create a meaningful link to the data being stored. Naming a variable X is terrible. Naming it player 1 high score is perfect. Just remember the golden rules for Visual Basic. Strictly no spaces are allowed. You should always start single words with a capital letter, and if your identifier uses multiple words, capitalize each new word.
Section 2. Global versus local scope. Now we're escalating the stakes a bit, because this is the exact tricky mechanic where our earlier student lost their marks. Scope dictates where a variable lives and who is allowed to talk to it. It's a vital difference that separates good coders from truly great ones. Local variables are incredibly secure. They can only be accessed within the specific code element or a single routine where they are declared. This drastically cuts down the risk of accidentally messing up their values from somewhere else in your program. Global variables, on the flip side, are declared entirely outside of any specific subroutine. That means they can be accessed and modified from absolutely any routine within the whole program.
Section 3. Visual Basic Arithmetic Operators.
Storing data is pretty useless if you can't actually manipulate it, right? To create programs capable of performing numerical computation tasks, Visual Basic relies on these 4 fundamental operators. It's super straightforward, but precision is key here. Addition uses the plus sign, subtraction uses the minus, multiplication relies on the asterisk, and division uses the forward slash. You're going to constantly use these operators to take values held in one or more variables, process them, and then store that new output right into a resulting variable.
Section 4, Top Band Exam Answers. Okay, now for the absolute climax of our explainer. Because knowing the facts just isn't enough. You have to package them exactly how the mark scheme demands. To stop losing marks, your answers must follow this specific high mark framework. You start with the core definition. Explain the exact technical mechanism, apply it directly to the scenario you're given, state the consequence or advantage of doing it this way, and finally, wrap the whole thing up using precise examiner wording. It is a brilliant logical staircase that leaves absolutely no room for the examiner to deny you your points.
And here it is. Matching your answer structure to these exact command words is that secret examiner clue I teased earlier. Think about it. The question didn't ask the student to simply state what a variable is. It asked them to explain how the program stores the high score. Explain specifically demands the why and the how. You have to provide the reasoning. If a question says evaluate, you've got to apply it to the specific scenario. Literally, ignoring these command words is the #1 reason students drop entire letter grades.
So let's play a quick game of spot the error and return to that flawed answer from the beginning. It uses a variable to save the score so everyone can see it. Based on everything we just covered, what is missing? I want you to predict the correction using our new knowledge of scope, strong typing, and the explain command word framework. Look at the phrase, everyone can see it. That implies something about scope, doesn't it? But it completely lacks the technical vocabulary. And what kind of data is a score anyway? The answer doesn't even say.
Boom. Look at how applying our framework and precise wording completely transforms that vague, zero-mark answer into an examiner-approved top-band masterpiece. We replace the weak everyone can see it with a global variable, declared outside subroutines, allowing access across all routines. We applied strong typing by specifying it's an integer, and we used a proper rule-abiding identifier, player1 high score. This doesn't just casually answer the question, it scientifically proves to the examiner that you fully understand how Visual Basic allocates memory and scope.
Section 5. The next locked room.
We've absolutely cracked the code on variables, strong typing, and scope today, but honestly, this is only half the battle. Real quick, to excel in your Cambridge examinations, make sure you subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS right now. We are constantly breaking down the exact mechanics you need to hit those top grade boundaries, and you do not want to miss these mark-saving frameworks.
Because to fully conquer Paper 2, you have to know how to evaluate complex algorithms once all those variables actually start interacting. Think about it. Your code compiles, your variables are strongly typed, but what happens when a user inputs massive, totally unexpected numbers? Do you know the framework for that? This final room remains completely locked until you join me in our next explainer on the top band evaluation framework. It is your mandatory next step to securing that top grade. So what exactly happens when your perfect code meets imperfect data? I'll see you next time to find out.